Hmm. Oh. Oh, okay. Oh, let me call out. We'll start in 3 minutes. 线上的人可以留个言吗？好 ，Then I think we will start today's lecture on types. So the word type just means ordinary data type like integer, double, string, and but before we start today's lecture, there are some announcements. One is this Gitter channel is where I post all the slides, video, and streaming links. So if you miss one of the class and you want to know, you can go back to find the slides. Yes, and I will not be private messaging anyone about the streaming links in the future because there is a lot of people I need to message in this case. So please go to this Gitter channel and check on the streaming links. And I will. Yeah, okay. So another one is Notion. We have all the syllabus posted on Notion, so you will know what this week is about. And third is we have a Google Calendar event. And if you want to be notified, you can send your email to me so I can add you to the lecture event. And in the last lecture, someone asked me to share the slide. If it's possible to share the slide before the lecture. And I realized that Gitter cannot share slide. So if you give me your email, I can email the slides through the Google Calendar. So if you want to be notified and getting the slides before the class, you can let me know. Yes. So I think that's it. And so when we think about type, we have this question. Let's look at something that looks irrelevant first. So how do you define things and what they are? This is the core question, and this question can be very philosophical, but here we talk about this topic in a more engineering. We restrict our discussion to engineer. So it is quite common, both in engineering or in philosophy, when we try to understand a thing, we define it in terms of its simpler structure. Meaning we want to understand a thing through its composition. So, for example, what is a rational number? Rational number is a 有理数. So you can explain to a kid about what's an integer, right? An integer is something that's not. It's something that's not natural. Like, let's not worry about rigorous mathematical definition. An integer is something like 1, 2, 3, 4, 5. So we can describe how many objects there are. Maybe there are 3 apples or 4 pieces of pizza. So that's kind of like integer. Let's assume a kid understands that. Then how do you define a rational number? You can then start by saying that if we have if I have 5 apple, and I give you 3, how many do you have now? And we define that ratio by some identity called rational number. So in this way, you see, a rational number is defined by 2 integers. One is numerator, another is denominator. Denominator tells you the total amount. Numerator tells you how much out of the total amount is specified in this number. So here we have an example of how do you understand a complicated concept through its decomposition, through a simpler construct like integer. And we can also understand it through its meaning. Its meaning would be how something is used. What's the physical meaning about it? How do you explain things intuitively? So what the explanation I give to integer is kind of based on its meaning. I didn't define it based on its it's a simpler construct. So if you are a math major, you will learn things. You will learn set. You will learn from set what is a set, and you will learn axiomatic set theory, and then you will construct integer out of set. Then you will construct rational number out of integer. Then you will construct real number out of the rest of the number, and that's how you get everything else. So the only intuitive understanding you need to have is it's a very basic layer. But now if we talk about integer, we can say an integer is a indivisible entity that would give its meaning. Or you can say an integer 1 plus an integer 1 equals an integer 2, which is twice the amount of the integer 1. Then these are kind of trying to understand the meaning of what things are. And third, we can understand a thing by its consequence. So sometimes it's hard to further decompose a thing or understand its meaning. One example would be if I ask you what is distance. What is the distance? You might be tempting to say that you might be tempting to say that distance is maybe it's the length of the shortest path between 2 points. Yeah. Yes. So this sounds okay. We say a distance is the length of the shortest path between two points. This is kind of now we are destructuring this concept of distance. But then you need to ask further, what's the definition of length? What's the definition of path? What's the definition of shortest? What's the definition of shortest path? What's the definition of points? And then you go on deconstructing things. So mathematicians find a very efficient way of discussing things, not by its meaning, but by its consequence. So we no longer ask, what is the distance? We ask if a space have the concept of distance. Let's not care about what it is yet, but let's define clearly what are the consequences of having such property called distance. So we say if a space has distance d, it's a function from 2 points to a real number such that the distance between something and itself must be 0. The distance of some x and y must equals the distance of y and x. And for every z that exists in this same space, we must have the distance of x and y less than equal to the distance of x and z plus the distance of z and y. So, but I mean, it's less meaningful. It's hard to say why these conditions are sufficient, why these definitions is able to represent the concept of distance. But the benefit is it's very clear. You no longer worry about the ambiguous meaning. You have a clearly defined consequence. of something called distance. So for understanding a type, you also can start from these three approaches. First is we still want to understand the meaning of the class, although meaning is not something that's well defined, but it giving you an intuitive understanding is important. And usually we ask about what's the role and responsibility of the class of these type. How do people use the type? What kind of entity does it represent? And then we check for its composition, what are the more basic types that form the type. And then we check on its interface. Its interface, you can say it's the consequence of the type. Being this type, what kind of operation it supports, and what kind of input-output does it take. So these are the very general concept of understanding type. And now let's skip the more philosophical issues. So today's syllabus, there are three main parts. One is we spend very little time look at basic types. And there are a lot of basic types, but we're only looking at numerals, pointer, reference, and function. And one of the major type is called also a string. But from my past experience, I know if I want to finish the lecture in 1.5 hours, I need to make the content short. So I only talk about these three types. And then we talk about some type interaction, which is more interesting and a bit more complicated issue. And then we have different typing strategy. So these are today's syllabus. On to the first one, basic types. So the most common type is probably numbers. But if you don't come from a CS background, you probably don't really know how numbers is represented in our computer, because our computer can only store 0 and 1 digit, so it has to have a way to represent a number as these 0 and 1 digit. And the way it does this representation is through this binary format. So just briefly explain about what's binary format. If I have a bit string like this, how you translate it to a decimal number by taking the last bit. This would be 1 times 2 to the power of 0. And this bit represents 2 to the power of 1. And then so we get this, and then this is addition, sorry. And then we have this again. We have 1 times 2 to the power of 2, and then what? Okay, and then we have 0 times 2 to the power of 3, and then we have 1 times 2 to the power of 4. This is how you understand a binary representation. So this thing add up to 1 plus 4 plus 16, so it's 21 in the normal decimal representation. But the problem with this representation is here you realize it can only represent positive integer. So usually they add a sign bit indicating if it's positive or negative. And but even that, then the representation is kind of limited to how many bits can add up to. So they add something called an exponent. This would be this exponent would be the number that would okay. So this Matissa would be explained this way, and the exponent will also be interpreted this way, and we take these two parts and we multiply them. That's how we are able to represent a large number in a limited number of bits. But yeah, and then we have sign. So that's usually how a language represents a real number. Now, so far so good? But given that, then there is the problem of overflow and underflow. Because as you can see, we kind of we cannot represent all real number. All possible number are just represented by all permutations of these bits possibilities. So we have the problem of overflow and underflow. So how do we deal with this kind of issue? First is learn about your language's specification, because some language have a specification, like they will tell you their double is represented by how many bits and how. So in that way you kind of know the limit, the limit of its precision, and then but some language doesn't. Language like C and C++. Oh wait, language like C, the C programming language. A lot of people think integer is 32 bits long, and long is 64 bits long, but that is actually wrong, because the language specification for C didn't tell us anything about how many bits that number should have. It tells us about how it's represented, and it tells us some limit, like long has to have a larger or equal range than integer. That's all. So you have to learn your language specification first to understand the limit. And sometimes you can avoid things programmatically. This is an example in our real code base. So when this is a condition to determine when we want to downsample a data. So when the data has too many row plus columns, a row times columns, we want to downsample it. And if it's not, then we keep the original data. And let's say our maximum limit is this number, which is the maximum number of integer. Now, this piece of code is then wrong, because this multiplication could easily exceed the maximum integer. So this condition would never be met. But one thing you can do is you can try to you can move one of the number to the right hand side. So you are comparing if data.columns is larger than this number divided by data.rows. This makes the program less understandable. But if you understand this is just a technique to avoid overflow, then you would understand this piece of program. And this, to be honest, because Decanter AI is supporting to up to 10 gigabytes of file. So if you multiply the number of rows to columns, it actually exceeds this number easily on a large data set. So this is actually an important issue when we write a program. Okay. Then another problem is floating point error. Floating point error is it's a similar issue. Like we cannot have like previous one is talking about we will have like a maximum and minimum boundary of the representation. This one is telling that our representation is not always exactly the number we want. So in this example, we want to check if a threshold is larger than equal to 0 and less than equal to 1. And this seems like a normal piece of code. But due to floating point error, it might not be this might not always happen. The bit representation might not give you a representation for 1. So you need to define an error margin. So the way we can check for a condition like this more safely is to require if the threshold is larger than equal to the lower bound minus a margin, and smaller than upper bound plus a margin. So this would be the normal way of doing this kind of floating point error check. And there is another more hacky ways. You can format your number to a lower precision. if you are pretty sure that the bit representation is going to be accurate to the 0.2 precision, then you only check if this number is larger than equal to 0 or less than equal to 1. But there is a catch here. The catch is here we format it to number, format it to string, but then problem could still happen in the to double place. So this might not be safe depending on your program's context. But these are just some of the ways you handle with floating point error. Okay, so so far so good. Okay. Now another kind of type that's pretty common is pointer or reference. Some language doesn't have pointer, and in C++ it's a hard concept to distinguish two. When we had a semester of C++, and half of it is about how to get the pointer and reference right. But in modern languages like Python or Scala or JavaScript, usually you don't deal with a pointer. You only deal with the reference. They kind of have the same concept. They are both something that points to other thing. So pointer is an address. The address denotes the location of another variable. And reference is also like a location that denotes to another variable. The only difference is for pointer, if you want to get to the other variable, you need to do it explicitly. So there is usually an operator for you to explicitly say, do you just want the address or do you want the content that's pointed to by the address? But for reference, you usually never get the address. With the reference, you can only use it as the content itself, but you have to know that it's pointing towards that reference. So many reference they can reference to the same object. So let's look at this piece of Python code. So here we define a function called reassign. Inside the reassign, it assigns this variable list to 0 and 1. And we also define this function called append, which append this list to 1. So what would happen here is when we call the reassign list, this list yes. So when we call this reassign list and then print the list, will it print out? Will it print 0 or 0, 1? And here you need the concept from last lecture again, too. You need to know how Python does scoping. You need to know how Python does scope and the variable resolution. So for Python, this list okay. So when we call this function, this list is a reference to this one. That means this is a reference to this one indeed. But when we do the assignment, this list has nothing to do with this one. So you are simply creating a local variable list. So you're not affecting the outside list. And when you do the print here, by our scoping rule, it searches for a list in the same scope. So it finds it here. So it prints out 0. This is what it prints in this example. Oh, I do encourage whenever you learn a new language, you should be able to answer questions like this Because if you are unable to answer a question like this, then you don't even know the language. You don't know how language gets its variable. So you are unable to trace the code properly, and you are unable to design and reason your code properly. So when you learn a new language, you want to understand if it's dynamic scoped or statically scoped, and you want to understand how they represent their data structure. When do they use reference? When do they don't use reference? So you know who is who. And this is just an example of Python. And now let's call append. Now we know that list is still 0. And when we call append, this list, again, this list is in the same scope as this one. So when we're inside the append body, this list is this one. And now we call append list.append1. This will modify the list in place. So this list object is a reference towards a place where we actually have a 0 and 1. And when we call append didn't change the reference, it changed the object that's being referenced to. So it changed this thing to 0, 1, 1. But it didn't change the reference itself. It's still referenced to this location. So after you call append and you print it, it will print 0, 1, 1. Sorry, it will print 0, 1. Oh, I'm marking the wrong arrow here. Yeah. So what I want to say is this list here. This list reference to an array of 0. Yeah. So when we call append, this list is this list. When we call append, this list is this list, which reference to this list. And when it's performing the append, it adds a 1 to the end. Yes. So but the reference is not changed. So it's still reference to this location, which becomes 0, 1 now. So when you print it here, it will print out 0 and 1. It's a very easy example, but just you want to make sure you understand how everything works under the hood, how everything is referencing to each other, and who is changing what. Yes. So that's the challenge of understanding pointer and reference. But luckily, all modern languages are usually just a reference. But still, you want to understand when are they referencing the same thing? When are they not referencing the same things? Because when you change a variable, when you change a reference, a lot of time it's dangerous. Because when you change a reference, other people might be referencing to the same thing. So you might be changing the content of other functions. So changing a reference might be dangerous. But that's just dangerous for JavaScript and for Python. It's not so dangerous for Scala. Because Scala, or I should say, it's not dangerous for immutable data structure. Because if something cannot change, it doesn't hurt if they share reference. So yeah, so that's a very brief note about all these. And then I want to ask about the previous slide. Yeah, we do want to assign something for the reference value. How can we do that? Because you can't.
We can't.
Yeah, reference is not something you can change. You can only change its content.
Okay.
It's not strictly defined that way, but usually, as far as I know, I see all programming languages designed that way. Even C++, if you have a reference, you cannot change the object of its reference. You can only change its content. It's not like a pointer where you can now let it point to other place.
I see.
Yeah.
So the only way we can do is just to remove all the content and append all the content inside.
Yes.
Okay.
Yes. Exactly. Okay. Now functions. Some of you might not be so familiar with function as type, but this is quite common in modern language design. For users like C, C++, they think function is a different thing from type. Like type are int, double, boolean, and function is function. But for modern language design, you need to understand function as a type. Before I go to definition, let's look at some very simple example. This is also an example very common in machine learning. Like here, I define a function called square loss. Square loss is a function that takes two double, and it returns you minus the two value, and you take the power of 2. So that's called square loss. And the type is let's write the type notation like this. It means it takes two double and return the double. That's the type of this function. Okay, but you can have more complicated function type. For example, we want something called a optimizer. A optimizer first takes n, which is the degree of your error, and then it takes these two number, and then the error is defined by minus these two number to the power of n. So in the case where we want a power of 2, this is called a ridge regression. We can get a loss function from this optimizer of 2. So this optimizer has a type of int, to double to double. But after you call it first time, it returns a function that's with the type of double to double. So the original type of optimizer is this whole thing, and but it ended up become after you call it once, it becomes the later part. Yeah. So you these are the common notations of a function as a type, and should be familiar to people with experience on modern language. So the idea is that a language should define some primitive type like int, double, and string. Then we define function as a kind of type denoted by type, right arrow, type. So the definition is extremely simple. It's just a type and a right arrow and the type. This is called a function type. So this means this is a function. Why? Because now function is a type, so this whole thing is a type. So this whole thing is a type, and the type to type is a function. So this is a function, and this is also a function because now this is a type, because function is a type, and type to type is a function, and function is a type. So this is also a type. So just by this simple composite definition, you are able to say a lot of complicated functions are type. And then your programming language has the ability to work with a whole bunch of complicated function. So a function is just I might mistype here. A function is just a type that support the function call operator. And what does the function call operator does? If a function is a type of type 1 to type 2, and x is a value of type 1, then f of x should be evaluated to something of type 2. That's the interface of function. So here you use the previous concept we mentioned. You don't really have to know what the function is. You only have to know what the function can do and what are the consequences of operating on the function. Then you can reason on your program. So okay, so far so good. We're done with some of the basic types. Okay. Then onto the more interesting, or we can say complicated part about type interaction. So first, let's talk about type coercion. Type coercion type coercion is an attribute of a language. It's if a language support a type being used as another kind of type without user explicitly change the type, then we say it's a type coercion. So if type A can be treated as type B without user writing any extra code, then we say the language support type A coercion to type B. And the most famous coercion, I think, is JavaScript. JavaScript support all kinds of coercion. You can write all this code. In a normal programming, you shouldn't write this code. So if Chloe, you write anything like this, you will receive a comment ask you to change it. But this is just demonstrating how much type coercion JavaScript support. The reason why JavaScript does it is because the original philosophy of JavaScript is because it will be run on a lot of different browsers, and you want to make sure your code just runs on different browsers. It's a very simple mindset, so they are supporting a whole bunch of these kind of things. And so you can have true plus false. In this case, true becomes 1, false becomes 0. You can have 12 divided by a string of 6. In this way, the string of 6 will be converted to integer 6 and then do the division. So I'm not going through all the conversion because this lecture is not about JavaScript. So the implicit type conversion, coercion, is a double-edged sword. It's a great source of frustration and defects, but also a useful mechanism that allows us to write less code without losing the readability. So yeah, here is the definition of type coercion. And type coercion is something, when you learn a language, you want to understand what kind of type coercion is support and what it doesn't support. Because that would be more implicit, and sometimes that causes a bug. But now there is another kind of type coercion that can be implemented by user. So this is the more interesting part I want to talk about. And for people from Python and JavaScript background, you are not going to be familiar with this user implemented type coercion. But for people who wrote C++, Java, or Scala, it's quite common, because these kind of if type coercion is defined by language level, then it only supports primitive type coercion. But in a language that supports very rich OOP design, you will be implementing a lot of your own class. And when you are implementing your own class, you want to define some type coercion relationship between your own class. So language need to give you give support for user implemented type coercion. So I will just give 2 examples here. One kind of scenario where type coercion might happen is it is used to reduce OOP operator overloading complexity, and I'll give examples later. And it can be also used to create domain-specific language, which I will also do case study later. So let's look at the first case study. If you define a rational number, so a rational number has a denominator and has a numerator and denominator, as we talked about. It can be simply defined by 2 integers. And let's say we only care about the plus operator for now. So if we write a rational number in a OOP fashion, a rational number addition operator takes another rational number, and after you add them, it should return another rational number. And the definition here are from our elementary school mathematics. So how do you do addition of 2 rational number? For the denominator, you take the denominator of left-hand side times the denominator of right-hand side. For numerator, you take the denominator of left-hand side times the denominator of right-hand side plus the denominator of left-hand side plus the denominator of right-hand side. That's how you Yeah, let me write it out. Like, it should be. You should learn this from elementary school, and if you didn't, it's really bad. So after you define this operator for rational number, you can initialize two rational number, R1 and R2, and you can add them. Just a note here, Scala support this kind of amazing shorthand to make things like really like a natural language. But what this means is R1, it resolves the plus as a member function of R1 instance and calls this function on R2 as a parameter. So R1, so this expand to R1 point plus left parenthesis R2 right parenthesis in the actual compiler code, but it gives us this syntactic sugar to write things in a more simple way. Okay, so this given this class being understood, now let's look at another kind of class we can define. It's a complex number. Now you probably only learn this until university, but the complex number is easier than rational number, because complex number consists of a real part and an imaginary part, and supposedly they should be able to be real number, but just for the sake of giving example, let's assume that we have the real part can only be the rational number we defined above, and the imaginary part can also only be a rational number. So a addition, for a complex number, the addition is just it takes another complex number and returns a complex number. So addition takes two complex number and merge them into one complex number. And the way you do addition is if you have a complex number a plus bi, another c plus di, if you plus them, you just add the real part together and add the imaginary part together. That's how you do complex number addition. So that's how it's defined here. It's also very simple. Then you can do addition. How? And now the problem is, let's look at the first problem. Back here, you see how complicated it is to initialize a complex number object. You have to, because a complex number object takes in two rational number, so you have to make up two rational number inside here first, then you create a complex number object. But if you look close at the two rational number, sorry, I have typo here. Should be 1. Yes. If you look close at these rational number, this is just a 1. This is also just a 1. This is a 1. This is a -1. So the problem is, can we construct complex number easier like this way? Can we do that to make the library more usable, more friendly? And let's look at some strategy. First is you can define a function called toRational. That's the people who start learning function would kind of do things this way. This toRational takes input as an integer, returns a rational. So how do you do so? You just put the denominator as this n, and a denominator as 1 and denominator as n. So you could make things a little bit easier. You can manually convert 1 to a rational and 0 to a rational. So this is attempt 1. But still, it's not quite what we ask. We want a very beautiful, complex 1-1 expression. So attempt 2 would be you do constructor overloading, or you do a generator pattern, depending on what kind of language feature does your language support. You can define another constructor overloading. So it takes two integer, and inside it does the dirty work for you. So then you can do things like this. So this wouldn't call the default constructor. This would call this overloaded constructor. And compiler knows that, because compiler look for the default constructor and realize you're not passing what we want. So it look for other things that might be legal, and then look for this apply and realize, oh, it's legal for your type. So it use this one. So this is attempt 2. But the problem is, what if I'm really naughty? I want to initialize something with an integer and a rational number, or a rational number and an integer. What if I want to do all these? Because if you support initializing with integer, you should support all kinds of combination. So the full solution would be you ended up writing a huge amount of constructor overloading. You write one for integer, one for integer rational, one for rational and integer. And then the default one is rational. Yeah. So for this case, you finally is able to support all 3 cases. But it would be nice if you have a user-defined type conversion from integer to rational number. And in Scala, we write an implicit function. This is a normal function, except we add an implicit keyword. And the function takes input a integer and returns a rational number. So the way this implicit conversion does is when the language look at a type and found a type mismatch, like if a compiler find a type A trying to be used as type B, it look for if there is any user-defined type conversion from A to B. If there is, then does the conversion. And if not, it's still legal. It's still illegal. But so this defines a type conversion from int to rational number, and then we can just naturally support all these, because for this case, compiler find that for complex taking 1, but this requires to be a rational, and the integer is not a rational. So it looks for if there is integer to rational type conversion, and finds the user-defined this implicit function. So it uses this function to perform the conversion, and then and then it can call this complex function naturally. So, but the takeaway here is no matter it's a user-defined type conversion or a language support type conversion, as a good programmer, we want to know about it, because there are someone who does the conversion. For interpreted language, it's performed on runtime. For compiled language, it's compiled to extra assembly code. Either way, that's extra line of code doing that stuff. So if you're doing, let's say you're iterating through an array of like 1 billion elements, and within each element, you are doing a whole bunch of type conversion. That's a lot of extra work for machine or for your interpreter. So that's also a motivation why we want to learn about type conversion. Not just for better design, but also knowing how language works under the hood. Okay, let's look at a more interesting example. Remember we have defined remember we have defined addition for complex number. What if we want to add a complex number to a rational number? Because supposedly a rational number is a subset. Rational number is a subset of complex number, so we should be able to add rational number to complex number. And now a very intuitive approach is, again, you define a global function called add. It takes in a rational number and takes in a complex number. And how do you add that? You create another complex number whose real part is the original complex number's real part plus this rational number, and the complex part is is still the original complex part, because rational number is only in the real part. It doesn't affect the imaginary part. Okay, so now you can add a R1 with C1. But then what about if you want to add C1 to R1, R1 to R2, C1 to C2? What if you want to support all the combinations? You need to create a whole bunch of add, and then you have a whole bunch of add in your space. So this becomes a bad design. And imagine then you have a third type. Let's say you finally come up with a way to define real number. Then you need to add, it's a C3取2. You need to define 6 kind of add. Yeah. Okay, then let's look at rational. Yeah, let's look at another approach. So let's say you do it in a OOP way. You have defined a plus for in rational number. You have defined the plus for rational. Now let's define a extra plus that can take a right hand side as a complex number. But a rational number plus complex number must be complex, so its return type is complex. And similarly, in complex number class, you define another plus to take in rational number. So this way, you can finally do R1 plus R2, R1 plus C2, C1 plus R2, and you can even chain your operation. That's another benefit. Because after C1 plus C2, it's a complex number, and complex number has a method of plus a rational number. So all these become legal. So this seems, we get everything worked, and our operator are contained within the class. So it looks like a good solution. But the problem is, if we have n class that can be added together, we need n plus function defined in each class. That's a lot of duplicated work. Right now it's just 2, so it doesn't seem too bad. So, and whenever we add one more class, we need to go back. Like, let's say we now have n class, and now we want to add n plus 1 class. We need to go back to that n class, and each one of them implement the new addition operator to the new class. So we need, and to that new class, we need to implement n plus 1 addition to all the existing class, including itself. So it makes the code very not maintainable. And what's worse is, let's say now we don't support just plus. We want to support another operator like multiplication or division. Then you need to go inside each class and implement that new operator n times. So you need to implement n times n new method. That's a lot of work. So that's why this approach is still not optimal for us to design operator. So far so good. Because I need to explain how we can do this without type coercion, and why they are bad solution in this scenario. So we can give a good motivation for user implemented type coercion. Okay. Now, finally, let's just if we can just define type coercion. We define a type coercion of int to rational. Then we define a type coercion from rational to complex. Then we don't have to do anything else. We can just have this operation naturally. So that's how elegant type coercion solve this issue. And let's go through how these kind of things work. The example here is actually we actually have more powerful thing. We can do something like this. We can write something like this in our code now, and the way this work is now compiler look at this R1 and 1. It cannot find any operator that takes in integer as parameter, but it can find an operator that takes rational as an operator. So it check for coercion. Are there user-defined coercion exist to convert integer to rational? And it finds it here. So it converts this one to a T1. It's a temporary variable generated by compiler. So now it can perform the addition here. And then you look at this T1 plus C1. And now now this is a different step now. So listen very carefully. So this is the rational type. It cannot find any addition that takes into a parameter of type. Oh no. Okay. Let me rewrite it. Plus 1. plus C1. Okay, so now we already know that this part get converted to a rational type. It looks into the rational's addition. It cannot find anything that takes input as a complex type. So first, it looks for coercion. Is there a coercion exist from complex to rational? But it search. No, there is no such coercion exist. There is rational to complex, but there is no complex to rational. But then it's really smart. It further look, are there any type that has a plus operator that takes in complex type? And compiler finds that, oh, our complex class has an addition that takes into a complex parameter. So then it check, can we convert this rational to complex so that it supports the right operator? And it finds it here. So it then change this rational to another temporary variable, T2, that's a complex type. And then it's able to do the addition. So that's just how compiler works and language works under the hood. But when you write code, you can just be very logical. So why do I say that? Because logically, integer can be treated as rational. You can establish that concept mathematically. You don't even have to think about program. And the rational number can be treated as complex number. You can just think about that mathematically. So establishing those two logical relationship, you design the type coercion, then everything should just work properly. So that makes that not just improve the program design, that also help us think. It help us think faster, help us think simpler. So this is how the concept of type coercion actually help you design a better program. Oh hey, KK.
Is there any cases for something conflict, like I want to do some increasing or coercion from rational to complex, and another coercion for complex to rational, and I also add an operator overriding for complex to
Yes.
add the plus function and rational
Yes.
plus function. I
Yes.
want to know the priorities for those things.
Yes.
Like,
So
we start do the coercion on right hand side first or left hand side first, something like that.
yes. Okay. So what KK is saying is, are there different ways of doing coercion to make things legal? And then you have to check on language. How does the language perform coercion? The language might be saying something like, okay, let me take Scala for example. If there is a type coercion exist, or let's say if there are two type coercion exist, both from T1 to T2. I mean, it's possible. Let's say you have an object, you want to return it as JSON string. And now you think, oh, let's just define a type coercion so that we have something from this object to string. But then there are another people who don't want to make it a JSON string. They want to make it maybe they want to make it a JSON string, but format it with a beautiful format. So they create another coercion. But both coercion go from that type to string. Then compiler would be confused. The compiler don't know which coercion to use. And in Scala, it just throws an error in compile time. Tell you that there are two implicit conversion exist. I don't know which one to use. Please fix that. So that's one possible way. So language would just limit those ambiguous situation. And another is they might be the language might be limiting the level of coercion that can be performed. So if I have a coercion from T1 to T2, and then I have a coercion from T2 to T3, then a variable of type T1 is used as a type of T3. Can we do coercion twice? Language will define that. And the easiest way is do not allow that. Because if you allow that, you need to check for circles. And you need to check for uniqueness, transitivity. So let's say we have a T1 to T2 and a T2 to T3, and the language allow you to do two conversion. but then there is another T1 to T3. Then should the language just use the coercion from T1 to T3, or should the language use coercion twice?
So if you the plus function, then we write two plus functions. One is for like a T1 and plus T2, and another plus function for T1 plus T3, and we implement two implicit functions.
Yes.
Two implicit coercion.
Yes.
For T1 to T2, T2 to T3.
T1.
So what will you do if I really use example for T1 and T2?
And what happen is like if you have a T1 at T2?
T2 or T1 at T3. Yeah, T1 at T2. Yeah. So will T2 coerce to T3 or T2 to T2?
Okay. So let's forget about this now. Wait.
No, it cannot. Yeah, if we really implement two plus functions.
So one way is the compiler finds T1 to T2, so make this T2, and then performs the addition.
Okay. So if we match and we won't do the coercion.
Yeah. But like if we support multiple layer, you can see how messy this can become. You can first change this to T3, and then change this to T2, then change this to T3, and then do addition. So for Ska, I choose the easiest way. It doesn't allow multiple layer of coercion. Doesn't allow ambiguous coercion. Yeah, I think it's a very good question. And these are the problem a language designer need to think about. So they have all theorems and all the mathematics worked out and prove that these property all proved out. And then they write the language so we can use it with confidence, knowing nothing strange will happen. Okay. And let's look at another case here. Okay, so far so good for this example. Type conversion, the use case for type code conversion, and now let's come to this case. This is where when we want to define a domain-specific language. So a domain-specific language means you create something that's written in a way that's understandable in a certain domain. But you are not creating a new language. You are creating this syntax built on existing language. So you're not writing a whole new language, writing a compiler for it. You are just creating a syntax out of existing language that makes you write code that's really understandable for a certain domain. And let's just look at this example. It'd be easier to understand what I'm talking about. And it's unit test. In unit test, we often want another kind of language. Here is a problem. The problem is we want to remember the problem we had when we are looking at the floating point error. If we have a threshold and we want to verify if it lies within 0 or 1 with we want to know if the value lays within the range. And I actually made a mistake on the first attempt. Sorry, there should be a minus tolerance here. There should be a plus tolerance here. Yeah. So if we don't think about anything let's just write our code in the old-fashioned way. We can just check for the condition if it's close enough and expect this to be maybe to be true. So that would be the old ways of writing it. And But you find this is used a lot and you want to make it more understandable, maybe you will define a function called approx, shorthand for approximate, which is how this is how PyTest and the JUnit test, they both do it this way. You create a function that takes in a value that's supposedly should be the answer, and the expected value that should be that the value that's the actual value and expected is the answer, and then a tolerance that's the area that you can take, and then inside you abstract the whole comparison logic inside the function. Then you call the function here approx with the proper value, with the threshold expect to be 0.5 with a tolerance of 0.5. Oh, then I didn't make a mistake here. Okay, anyway, so both attempts are fine. They use features supported by the original language, and you can write things like this. But the problem here is still, if we don't look into the definition of approximate, how do we know which number to put where? I mean, here we have good variable naming, so you can probably guess it, but it's still not very optimal. Now, what if we can write something like this? It would be then easily understandable even if you don't write in the language, because this tilde equal is people understand it as approximate usually in mathematics, and 0.5 plus minus 0.5, that's like an expression. So this is what I mean by domain specific language. Like, I'm not creating a new language. This is a completely legal Scala syntax, and I can show you how a type conversion might be able to achieve this. So this here I write a implicit class, and in Scala there are two ways to define implicit conversion. One is like define a function as we demonstrated, and another is when you define a class, you write a implicit here, and the class takes a double as input for its constructor. And since it's a implicit class, it means we now installed a user-defined type conversion from double to this class called StatMatch. So now there is an implicit conversion that exists. Okay. And so here, th is double. The compiler look at double, doesn't see any operator of tilde equal. So it look for other class to see if there are any other class that support the operation. And it realized that, oh, the class StatMatch has this operator. So the compiler then see if double can be converted to StatMatch by a type conversion. And since this is an implicit class that defines such a type conversion, so compiler create a T1 temporary variable. So this is a StatMatch. Yes. So now we have this first level of conversion. Before we look at this part here, let's look at the inner part first. So here we have a 0.5 plus minus 0.5. Now 0.5 is a double. Double doesn't have plus minus operator. So the same process go through again. Compiler finds StatMatch have plus minus operator. So it converts 0.5 to this temporary variable T2, and it's supporting this plus minus operator. And plus minus operator now takes in a double. This is legal here. So and so this whole thing then evaluates to a thing called range spec. And now it's finally legal. We call this T1 on this tilde equal function that takes input a range spec, and we indeed get a range spec as input. So the whole thing evaluates and then return a boolean. So that's how you that's kind of how you use the concept of type coercion to create domain specific language. And as far as I know, they usually this concept is the same for Scala or Ruby on Rails. Ruby on Rails is another example you would. It's popular for people to create a domain-specific language. I wrote that for 1 year. It's a bad language, but it supports this very well. Support you to define domain-specific language. Okay, so yeah, this is just a. So we talked about implicit conversion, but now there is also this explicit conversion. I never talked about it, but explicit conversion just means you write a function to do the conversion, or like previously we had some examples, like to rational. Here, oh wait, no. Like here, if you write a function to convert something, like this can be a global function, or it can be like a member function. Like you write a member function in a rational object and call like to complex, and then it becomes a complex number. Or it's pretty common in backend programming where you want to convert something to a JSON string, so you write to JSON function, so it converts to JSON string. So when you write something to do the conversion, it's explicit conversion. So what are the pros and cons of them? Here are some of the golden rules to help you decide when to use what. You want to use implicit conversion when we want to hide the conversion detail, and when conversion makes sense. Conversion makes sense means that's how people think about this kind of type. Like people think double. People would think integer is rational number. Rational number is complex number. That's well established in people's mindset. Or sometimes in business logic, there are also something like this. So when the conversion really just makes sense, people don't need to know about you are doing the conversion, it just makes sense. Then that's when you can choose it. And when each conversion is clear and unambiguous, this is what KK talked about. If you have implicit conversion, there might be some really strange thing that happen where converting things all around. So when your system of type is clear and unambiguous, you can also use it. And this is not a or, this is a and. All three condition has to satisfy for you to use implicit conversion. And but when do you want to use the explicit conversion? You want to use it when you want the user to be aware of the conversion. Like when we are converting an object to JSON and we want to prettify it. You probably want user to explicitly call these operations to get the results. So then that's when you do explicit conversion. Or when multiple conversion probabilities all make sense. Example being that I make the wrong example. So if yeah, this is the wrong example, sorry. But it would be more like if you have something like object to JSON, this makes sense. But if you have something like object to pretty JSON, like they both make sense, and they are both converting an object to string. And if you have multiple conversion, that makes sense. Even if you can decide just import one implicit conversion, not importing the other, to make sure compiler pass, it's still a bad idea because it makes your code hard to understand. So here are the golden rules, and so far so good because we are moving on to another topic. Hey.
So in Scala, is there any implicit language coercion in Scala?
Yeah, there are still some, but not as much as JavaScript.
Oh, I see. So, okay. So how do we know language? How many coercion in the language?
It's written in their spec. It's gotta be, yeah, they gotta be listed out 100%.
So
Yes.
can we say like for the language need to compile and we can sometimes we can have a user defined conversion, and if the language do not need to compile something like Python or JavaScript, and we cannot do the implicit we cannot do the user defined conversion. Can we say that?
Sorry, can you repeat that
I
again?
mean, there are two kinds of languages, right? One we need to compile, and the other is one need interpreter,
Yes.
and one need compiler, right?
Yes.
So for the language need interpreter, we cannot do the user defined conversion. Can we say that?
No. We can define that in any kind of language. Because at the beginning of the class, I already mentioned that every language can be implemented as compiled language or interpreted language. And you can actually prove that mathematically because they are both Turing machine. And the languages are representable by Turing machine. So compiled or interpreted, it both work. Yes. And what KK talked about make me think about another thing. That's when you look at the language spec, it has the supported coercions. But sometimes a compiler will have to respect that. But in the place where language spec doesn't talk about, compiler might decide to do its own coercion. So this will happen in JavaScript. Sometimes JavaScript didn't define its coercion, and then different browsers decide to perform the coercion in different ways. So don't blame the language. Oh yeah, you can still blame the language, but then you need to check on the browser. Yes. But for languages like JavaScript, I would say don't rely on that. If coercion is ambiguous, just make it explicit. Because even JavaScript supports coercion, you can still do something like string parentheses and like to make it clear that I'm converting this to string. So, yeah.
That's why some people use TypeScript.
Yeah, that's why TypeScript is really a thing. Yes. Yes, how it's hard to work with things that doesn't have a good type reason.
There's too many implicit conversion not make sense.
Yes. But there are people who don't have a choice. They need to understand this, like Alex and Cindy. They are DevOps and SRE, so they deal with Bash a lot, and Bash is even messier than JavaScript. It's a really messy world. So, but it helps if you understand. Also, Bash language does this dynamic scoping and does this kind of type conversion. So it helps to have those concepts in mind. So to know that it's actually not so many exceptions. There is actually still some rules that Bash follow. Yeah. So this actually I think this is the final topic. Yes. In this topic we talk about type identity and type equality. Intuitively, it's how do we treat two instances as the same. And this is a very important subject actually, because in programming there are two ways to treat two instances as the same. One is called identity. Identity consider two values are the same, if and only if they occupy the same memory cell. How do you know they occupy the same memory cell? You look at their address. So if you have an object and you copy it to another memory cell, then they are not considered the same in terms of their identity. But if you use a reference, if two reference to the same memory object, then they are considered the same because they are referencing to the same memory cell. And equality says two values are equal if their semantic meaning are the same. So it's important when you learn a language. because usually language support equality sign. What does the equality sign mean for different type? It might not be like the whole language consider everything in identity. It might be the case where they consider some type using identity and some type using equality. And let's look at an example in Scala. In Scala, if you have an array, see these two arrays are exactly the same. They both have 1 and 2 as the two only elements in the exact same order. But if you look at A equals B, it will tell you false. But if it's a list, it will tell you true. And why is that? Because array in Scala is a mutable object. Oh, actually, I'm gonna go to the next slide. Then I'll come back to that example and explain why Scala designed it this way. So, the benefit of comparing about type identity is it's really fast to compare. It's really fast because you only compare the memory address. If they're different, they're different. If they're the same, they're the same. That's why React use identity to decide whether to re-render. So the thing about React, if some of you don't not familiar, is React have something called component. These components are UI elements, and each component has something called a state. Whenever state change, component re-render. But how does React know the state has changed? Because state is just an object. It can be very, very deeply nested. It can be an object of A, which has A has an array. This array maybe has like 1,000 elements. And then it has B. B is another object that has C, which is another object that has a D that is a reference back to B, and all those are legal because you can put anything in the state. So how does React able to know state has changed? First is it's very costly if it's go down to compare if every key value are the same. Second is it's impossible because JavaScript allow you to mutate variable, so you can have circular data structure, and in that it's impossible to determine identity. So for React, it's simply check, did I change the state, and then I re-render. That's why in React you always have to create a new state object. You cannot just change the value in the state. That way component will not re-render. So yeah, so the pro of identities is fast, but the bad thing is it's not intuitive like the previous case. I don't know why is these two arrays not the same. It's hard to intuitively explain why if you are not a programmer who is aware of memory. Now on the other hand, equality is pro is it's intuitive and flexible. The con is it does not work for circular data structure, and it's less efficient to compare. So now this is what I want to talk about. It doesn't work for circular data structure. And remember in the very, very first lecture, there is a kind of language where circular data structure is impossible. It's called functional programming. If you use functional programming, it's physically impossible for you to create a circular data structure. And let me explain why. A circular structure must be something that they points to each other. But how is it if you have a functional programming where you cannot modify your data? You must first create this one, and then when you create this one, you can reference it, of course. But how do you then let it reference here? It's impossible because when at the time you create it, it doesn't know the existence of these objects, so you cannot create something that reference here. So by the time you create the second object, it's already too late. So you can only have single. Your data cannot be circular. So let's go back here, then we understand, because in Scala, list is immutable, array is mutable. So for mutable data structure, it uses identity. For immutable data structure, it uses equality. And that's the practical application. So if you understand the concept, when you learn React, you immediately know why it does things that way. And when you look at this kind of strange behavior, you immediately know why it's designed that way. So, and also when you design your own data structure, you probably want to think about, do you want the data structure to be comparing equal using equality or identity? That's also something that's programmer's responsibility to design if you are creating your own data structure. Okay, now finally done, and the last section is about different type strategy. And from my past experience, I already know I wouldn't have enough time. So this is simply a homework. You can look into what's the difference between a strong typing and a weak typing. What are their pros and cons? Which one is Scala, C++, JavaScript, and Python? Can we prove the above categorization? This is an interesting one. Can you use a piece of example code to prove that this is a strong typed language or this is a weak type language? If you can write a piece of example code to prove that, that means you actually understand what these terms are. And what's the difference between static typing and dynamic typing, and then do the same practice. What are the pros and cons? Determine these following language or just the language that you use, and prove it. Prove that, find a piece of example code that can prove they are actually static typed or dynamic typed. So that's all for today's work. And because any question? Okay. Because a lot of people join in the end, so I want to go back to the announcement again. Announcements are very important. And I just thought about one thing. At the beginning, I said there will always be a period of discussion after the lecture. But then I just give up because I don't know how to arrange that. I don't know how to manage the time well. I always spend about 1.5 hours talking. So I just give that up, but you are still free to stay for any free discussion. And then these are the important announcements. First is please use Gitter to see all the slides, video, and the streaming link. I cannot doing Facebook Messenger to everyone and email to everyone and maybe line chat to everyone to give out this information. So all information is on Gitter, and I will not be private messaging any link to any person in the future. And but as a programmer, I want to encourage everyone to start using Gitter. Gitter is a very active developer community. You can find a channel for Scala, a channel for JavaScript, a channel for Spark, and all that. And I think the good thing about it is it's different from Stack Overflow. Stack Overflow is where you go up and ask a question, and then you wait for a really long time for someone to answer, and you are not sure if they're on there. But Gitter is more like a chat room. So sometimes you get to really just start chatting to people about your problem. It's really nice, and it connects you to some of the very amazing people up there. Sometimes the language's author is in the channel, so you are talking to the author of the language. The author of the library, contributor of the library is in the channel. I've talked to CTO of H2O, talked to the chief machine learning scientist of H2O, both on Gitter. I didn't know who they are. They are just, for me, they're just someone who's chatting with me and solve my problem. And please use Gitter. So I encourage you to do that. And then Notion. Notion is where our syllabus is, so you can check for syllabus on Notion. And Google Calendar is, if you can give me your email, I can add you on Google Calendar so you get notified when class starts. So that's all. And thank you all for today's time. So we'll end the streaming then, and we'll have any discussion or question we can stay for that. 好，YouTube 的人，拜拜。